So yeah, that's pretty much all I have to say about Cartan's equations of structure right off. They're interesting, of course, and in a broader context, they're even more interesting. I'll try to come up with an example at some point where we have omega, wedge omega is not just 0, you know. But I would look at the spherical coordinate example in my notes, but I know it's kind of like, so I think we should go on to chapter 3. Now, I'll tell you already in my, I wanted to leave that actually, that's relevant. And so chapter 3 is on Euclidean geometry, all right? And so let's read you some snippets from the start of it. I say, the study of Euclidean geometry is greatly simplified by the use of analytic geometry, all right? In particular, R3 provides a model in which the axioms of Euclid are easily realized for lines and points, right? Like, for example, one of Euclid's axioms is that there exists a line segment between 2 points, right? Can you guys tell me what the line segment is between 2 points in R3? You should be able to, right? We have a formula for it. If I want a line segment that goes from P to Q.
Oh, I remember that. It has T. It's T of P plus
It's okay. So R3 with Euclidean distance. Forms Euclidean geometry, essentially. So what you're looking for is something like this. If we have gamma of t equals to p plus t times q minus p, this gives a mapping from 0, 1 to R3, which connects the point P to the point Q by a line segment. And so that establishes one of the axioms of Euclidean geometry concretely, right? There's the line segment, that it does it. In fact, we can explicitly prove that the other axioms are borne out, by R3 with our usual notions of distance and such. But anyway, this, has been available since about the time of Descartes, this idea of identifying space with numbers, right? Before then, they had these like synthetic sort of arguments, compasses and such, compasses, rulers, and logic. But anyway, we're going to study Rn as Euclidean space, and by that I mean we're going to give the distance between points by the following formula. So, definition, the distance from the point P to the point Q, it's equal to what? The square root of P minus Q dot P minus Q, right? Or you could also call that the length of the P minus Q vector, right? That gives us the distance from 2 points, from one point to another in Euclidean space, all right? And what we're going to see is that there's a natural family of functions which preserve the distance between 2 points under a mapping. And such functions are called isometries. We'll prove that those are just either translations, reflections, or rotations. That's what we're going to see. Now, I don't have too much to say about reflections in these notes or in this class, but if you were to go back and read that book that I mentioned at the start by Saul Stahl, in there you would find proofs that, in fact, the reflections are basic. And you can generate all of the other isometries using reflections. If you've got like a pair of reflections or something like that, it's sufficient to generate the group of isometries. And that's interesting in Saul Stahl's book because he then uses those same kind of arguments to generate the group of isometries in those non-Euclidean geometries, the non-Euclidean geometry of hyperbolic space, like we talked about briefly at the start. So the way I'm doing it today is not the only way. I'm pretty much following O'Neill, but I would just tell you that there's deeper group theory to learn here. All right. If you want to see an excellent presentation of the mathematics here from a group theoretic perspective, it's hard to beat. There's about four lectures in the abstract algebra series on YouTube by I think it's a professor from Harvard, and in about 4 lectures he does all of this and a lot more. It actually derives all the possible finite subgroups and such that are possible. It's very interesting. But what I do have in my notes, which is not in O'Neill, is there's like a section in chapter 3 on what's called, the Frenet frame in n dimensions, right? You could look at a curve in n dimensions and try to build a frame on it, right? We did 3 dimensions and we built a frame, right? Well, you could try to do that over for a curve in Rn, right? If you had a curve in Rn, you wouldn't just need a tangent, a normal, and a binormal, right? You'd need E1, E2, E3, all the way out through En. So there's another, and this is an excellent book for further study. This book here, it's Differential Geometry, Curved Surfaces and Manifolds, 2nd edition by Wolfgang Kuhnel. And in there, he has the extension of Frenet-Serre to n dimensions. And he talks about the Frenet-Serre formulas for, an appropriate curve in n dimensions, which essentially is one for which the, I want to say the first n derivatives are linearly independent. That suffices, I think, as a condition. Maybe n minus 1. If you take a look at what we did for the Frenet-Serre, we needed nonstop nonlinear. Nonlinear amounts to saying that the second derivative is not equal to 0. So, all right, I'm going to shut up about that. I'm going to actually skip that section because I don't think we have time in here, and it's kind of, I didn't give any homework on it either, I don't think. Go for it. Mm-hmm. Is that right? I bet you looked at it from like the viewpoint of the postulates and the axioms and that kind of stuff. Yeah, this is going to look quite different. So, all right. So let's get to it. Definition. We say f from Rn to Rn is an isometry of Rn when the distance from f of p to f of q is equal to the distance from P to Q for all P and Q in Rn. Now, I'm stating the definition in Rn. Of course, we're primarily interested in R3, but all right. So the first and easiest theorem we should prove about these things is the composite of isometries is an isometry theorem. If f and g are elements of isom Rn. Let me introduce a notation to save myself a bunch of writing today. I'm going to do isom Rn for the isometries of Rn, okay? And then f composed with g is also a isometry. Proof. let P and Q be points in Rn, and F and G isometries. Then the distance of F composed with G of P, comma, F composed with P composed with G of Q is the distance of F of G of P, F of G of Q, by definition of composition, right? But check it out. Since F is an isometry, right, and G of P and G of Q are points, since F is an isometry, I can rewrite this as the distance from what? F of distance from G of P to G of Q. Do you guys get it? Does this step make sense? It almost seems too easy, but there it is. But G is an isometry, right? So that's also equal to the distance from P to Q. So what do we have? We have the distance from F composed with G of P to F composed with G of Q is the distance from P to Q. P and Q being arbitrary, we have shown that F composed with G is an isometry. In fact, if you really take a step back and look at the idea here a little bit more abstractly, you could see that there's nothing really special about the distance function for R3 or Rn here going on, is there? If you had a distance function on a set, right, and you said that all of the mappings which preserve the distance between points on that set, whatever that distance was, right, if you said those things were isometries, it would still be true that the composition of isometries is an isometry. So this is not, in fact, really just a theorem about Euclidean geometry right now. This would also be true for isometries in like hyperbolic space or something else. I'm going to leave that. I feel like I'm going to need it. Oh, that's not a derivative, that's the distance function. Right, if I can draw it abstractly, you know, if we have P and Q, right, and then we think about F, you know, this is all, think of Rn as think of F as moving points to the same set. Think of the Rn and the domain and the target being the same Rn. Then whatever this goes, this distance and this distance have to be equal for an isometry. It preserves the distance between points before and after the mapping.
Okay.
So, I mean, once that clears up in your mind, you immediately know an example, right? I mean, like, as soon as you, so if we have TA from Rn to Rn by TA of x equals to a plus x, or x plus a, this is translation by a. So, I mean, a translation is an isometry, right? We can easily check it. Distance TA of P, TA of Q. I'll use the norm because it's easiest. So we've got P plus A minus Q plus A. See what happens? The A's, they be canceling. And we're just left with norm of P minus Q, also known as the distance from P to Q. So therefore, translation is an isometry. By the way, TA inverse is equal to what? If I want to undo a translation, what do I do? The backwards of it? Circle back? Let's see here. Not really circle back, just go back. So translate by minus A, right? So your TA composed with T minus A of X is what? TA of T minus A of X, which is TA of X minus A, which is X minus A plus A, which, by the way, is X again. And T minus A composed with TA is the identity on Rn similarly. Do you guys see this notation before? Identity?
Oh, we should see it in theory all the time.
Oh, good. So this calculation right here shows that TA composed with T minus A is the identity on Rn. And so we have left and right composition of the function gives you back the identity, which of course suffices to prove that TA inverse is T minus A. So every translation is invertible. Okay, so far so good. What else could we do? How about an orthogonal transformation? So here, we're going to be, this is a linear transformation, let's say R from Rn to Rn, such that the matrix of R transpose times the matrix of R is equal to the identity matrix. This is an orthogonal transformation. So, for example, you could have the matrix of R cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, 1. This is the matrix of rotation by theta about z-axis. This is a specific instance of a orthogonal transformation. You can check that if you multiply the transpose of this matrix by that matrix, again, you get back to the identity matrix. Okay? So, if, R is matrix of orthogonal transformation, then we say that matrix of R is an element of what's called ON. So, and this is the set of orthogonal matrices. You already got me? Okay. So ON would be like, I'll use A instead of R. I'm tired of writing R. A, n by n real matrix, such that A transpose A equals to the identity matrix. Okay, so we should notice something about this. If A is an element of ON, then A transpose A equals to I, right? Let's take the determinant of this. What do we learn about these? So to the determinant of A transpose times the determinant of A equals the determinant of I. What's the determinant by the product of the determinants rule, right? Determinant of the product is the product of the determinants. What's the determinant of a transpose?
Wouldn't it be like the I, like through the middle, with the diagonal, all the identity?
That is the transpose, yes, but how is the matrix of a, how's the determinant of a matrix and the determinant of the transpose of the matrix related? No? They're the same, right. In other words, I can just do this. In other words, what I have here is that the determinant of an orthogonal matrix squared is equal to 1, because the determinant of the identity matrix is 1. So what does this show you? This shows you that if you have an orthogonal matrix, you only have two choices for your determinant. The determinant of A is plus or minus 1. Here's another notation. SON is equal to A in ON such that the determinant of A is equal to 1. These are the so-called special orthogonal matrices. And in fact, these are the rotations. The transformations corresponding to these matrices, rather, are rotations.
So R, you said, was a rotation of theta.
Yeah.
So your theta would either be like pi over 2, pi, or pi over 2.
Could be anything. I mean, any real number.
And so does that map to like, or could that map to like something like a triangle rotating like 90 degrees or 60 degrees or something?
Sure, yeah, we could rotate a triangle 90 degrees, 60 degrees. You pick it, you like it. If we put theta equal to 0, we're back to the identity transformation, which is the same as T0. So like, there is a translation which is also a rotation. Yes, but that has the same formula as when A equals to 0. It's just T of x is equal to x. T sub 0 of x is equal to x. If I was to call this maybe R sub theta, just to give it a name, you know, so I can reference it better, then if I look at R sub 0, that is the identity transformation, because the matrix of that transformation is the identity matrix, which makes it the identity transformation. Now, I'm claiming these are rotations. Obviously, there's work to do there. Like, I have not shown that, right? But you can show it. And in fact, this matrix is interesting in that if you look at the matrix times E3, what do you get? Like E3, like or U3 in our language. Matrix times U3 is what again? right, it's U3 again. So if I do this matrix times 0, 0, 1, I get 0, 0, 1 back again. That means that 0, 0, 1 is an eigenvector with eigenvalue 1 for this matrix. So as you study these sorts of, and we have other theorems from linear algebra, right? What are the eigenvalues? What are the eigenvalues of a orthogonal matrix? Well, if we're talking about a 3 by 3 orthogonal matrix, then there are 3 eigenvalues up the multiplicity and allowing for complex. Since it's a real matrix, the complex values have to come in complex conjugates. But the product of lambda 1, lambda 2, and lambda 3 has to be 1. It has to be the determinant of the matrix, by the way. And that has to be 1. So that forces, and either they're all real, in which case they have to all be 1, 1, and 1, or 1, minus 1, and minus 1, or they have to come in a complex pair, and the remaining one has to be 1. So any way you slice it, there's always an eigenvalue with eigenvalue 1 for a rotation matrix in 3 dimensions, which is to say that there always exists an axis of rotation for a 3-dimensional orthogonal transformation with determinant 1. Now when you put determinant minus 1, there doesn't have to be an axis which is fixed under the transformation. An example in R3 of one which doesn't have determinant 1, which has determinant minus 1, would be this map. So zeros elsewhere. This matrix is minus the identity. And you can easily calculate that minus the identity transpose times minus the identity is equal to the identity, right? Therefore, minus the identity matrix is an element of O3, right? But this mapping is not an element of SO3 because it doesn't have determinant 1 as determinant minus 1. And in fact, this mapping is what we call a reflection.
So, negative y transpose times negative y.
I said T, I should use R here, right? Or something else, like, I don't know. I'll use S for lack of imagination. What is it?
So, that's not. So, negative x is equal to that matrix times the vector.
That's X, yeah. So, I mean, here I'm taking n equals to 3 for the sake of discussion.
And then, so that's negative the identity matrix.
Mm-hmm.
But if you take the transpose of that times itself, you get I back.
Right, and I guess I should do transpose to check the condition, right? I'm supposed to check that the matrix transpose, right? So I'm not being true to my... Oh, wait a minute, no. I'm an idiot. Yeah, that's fine. It was fine. It was fine. Anyway, that gives you minus I times minus I, which is I again. So it's orthogonal.
Yeah.
Okay. But it's not a rotation. And in fact, there's no... And you can tell something that's a rotation has to have an axis which is fixed under the rotation, right? So if you can't find an eigenvalue with eigenvector with eigenvalue 1, like that's essentially what makes a rotation a rotation. If you have an eigenvector with eigenvalue 1, that means that the transformation acting on the vector gives you back the vector again. Like that is quintessential for what we would think of as a rotation. It has some axis which is fixed. Actually, that's not. Or either that has to happen, or I should say that there's another possibility, which is there is no axis, which is just like the axis in some sense is like out of the page, right? Like rotations in the plane, what you want to be the axis is out of the page, right? But anyway, let me not get into this. This is like beside the point here anyway. What I'm trying to say, I've already admitted that my explanation for why this is a rotation and what we should call a rotation versus a reflection is somewhat incomplete. I'll just tell you this: determinant 1, rotation; determinant minus 1, not a rotation. Okay. Now, but my claim though is that orthogonal transformations are isometries. All right. Goodness gracious. Time flies when you're having fun. All right. So theorem. Orthogonal transformations are isometries. So proof, I'll get to the heart of it. So we should look at the distance, from R of P to R of Q, right? And to make life simpler, I'm going to square it. Since I've squared it, I have the norm of matrix R, well, excuse me, let's say R of P minus R of Q squared, right? But R is linear, so I can rewrite that as R of P minus Q squared. But the formula, and I can do better. I can rewrite that as the matrix of R, right, times that vector, length of that squared. Okay? And then I can say, aha, well, that's really just the vector matrix of R times P minus Q transpose times the matrix of R times the vector P minus Q, like so. Now this, if you've forgotten, remember that, like if we have a vector A dot vector B, we can rewrite it as like the A vector transpose times B vector if they're both column vectors. You guys remember this? There's a couple things I'm using here. The one is that the length of a vector squared is the dot product of the vector with itself. Something that's fresh on your mind from the homework, right? So using that, and using also that we can write a dot product as the transpose of the vector times the other vector, I have this. You guys on board? All aboard? Sorry, little train lingo. Now, well, R is a linear, it's a linear transformation. Linear transformation.
So it's just a map to
Yeah. So now, I use the sock shoes identity, which I thankfully have proved right over here. So I've got the transpose of the product of two matrices. One of them is a column vector, but it's still a matrix. So when I take the transpose of that, I get P minus Q transpose times matrix of R transpose times the matrix of R times P minus Q. Lo and behold, this, by definition of orthogonal matrix, is the identity. And what do we have? We have P minus Q transpose times P minus Q, which you can identify as P minus Q dotted with P minus Q, right? You're like, oh, now you're writing it. Yeah, less to right here, which is the length of P minus Q squared, right? Which is the distance from P to Q squared. Well, I changed from a matrix product to a dot product. The row column product is the same as the dot product of the column vectors in that sense. This is the transference between row column products and dot products. Now, if we look at this, we have this is equal to that, but distance is positive in both instances, right? So we could get the square root. We don't have to worry about plus minus. We get what? The distance from R of P to R of Q is equal to the distance from P to Q. And so therefore what? R is in isom Rn. At this point, we no longer need the sock shoes, so I'll erase it. By the way, I don't expect you guys to prove sock shoes in here, obviously. Like, you just use it, you know. Theorem. In isometry, fixing 0 is an orthogonal transformation. So let me state that theorem again. F in isom Rn with, I can see here, f of 0 equals to 0 if and only if f in orth Rn. I've invented a notation for the orthogonal. I'm calling it orth. Is this going to go in your book? Okay, so proof. We'll do this way first, right? So we just argued that f is orthogonal implies what? F is an isometry, right? So we got that. Orthogonal implies isometry. Does an orthogonal transformation send 0 to 0? Let me ask you a different question. Does a linear transformation send 0 to 0? It does, right. Because f of 0 is equal to the matrix of f times 0, which is equal to 0. All right, so yes. Great. So we're done with that direction of the proof. Now let's work on the other direction. So suppose f is an isometry which fixes the origin. In other words, f of 0 is 0. Now what do we have to do? We have to show that this origin fixing isometry is necessarily a linear transformation whose matrix satisfies the condition matrix transpose times itself as the identity. Think about what we have to work with here. What do we have to work with? So we don't have much to work with except for the distance function, right? So one of the things we can do is make some fundamental observations. Observe. So the distance from f of p to f of 0 is what? Well, it's the distance from p to 0, right? But this is also the distance from f of p to 0, because f of 0 is 0. So we get that the norm, or the length of f of p, is equal to the length of p. That's good. Apparently, f is a mapping which preserves the distance from the origin, right? Map spheres to spheres. That's good. Now, I say, so we have, this, by the way, also implies f of p, oh, come on, f of p is not identically 0, right? So there's got to be at least, I mean, p is not always 0, so f of p is not always 0. Great. All right, so next, we're going to go through a calculation. The distance from f of p to f of q squared is equal to the norm of f of q minus f of p squared. All right? Now, by a calculation very much like one you just did in your homework, this is what? This is f of q minus f of p dot product f of q minus f of p, right? And you take this dot product, what do you get? You got your f of q dot f of q minus twice f of p dot f of q plus f of p dot f of p. This first term is the norm of f of q squared. This last term is the norm of f of p squared, right? But what is that? I mean, this is equal to the norm of q squared, right? And this is equal to the norm of p squared by our observation before this. So that's kind of neat. And then, likewise, we can do the same calculation if we calculate the distance from p to q squared. We get norm of p squared minus 2 p dot q plus the norm of q squared, right? By the same calculation, without f, we get that. But these are equal. See, this and this have to match up because it's an isometry, right? So as you equate this and that, you can cancel this one with that one and that one with that one. And what you're left with is that minus 2 f of p dot f of q is equal to minus 2 p dot q. So we've stepped it up a notch. We had that the norm was preserved under F. Now what do we got? The dot product is preserved under F, right? That's pretty nice. Does that prove it's linear? It's not the same as linear, is it? I mean, I want to believe that that's enough, but we should probably give some evidence, right? All right. So here we go. Notice f of, let's say, ui dot f of uj is ui dot uj, which is Kronecker delta ij, right? Thus, f of u1, f of un is orthonormal basis. Rn. That's useful. Great. Now consider the following. Let x, y, z be in Rn and C a real number. All right. Then if we look at f of cx plus y dotted with f of z, what do we get? Well, we get cx plus y dotted with z, right? By the identity that we have. But let's see here. But this, of course, is c times x dot z, right? Plus y dot z by properties of the dot product in Rn. And working back, that's c f of x dot f of z plus f of y dot f of z. Again, using our we call it star by star again. But now we can use properties of dot product again and factor out the f of z, right? So we've got c f of x plus f of y dot f of z. And I would emphasize here that this identity holds for what? This is for all f of z, right? So what do? This is an orthonormal basis, right? So if you just let z equal to, uj, and let j equal 1, 2, all the way through n, you get that the components of this and the components of that, the jth components of this and that with respect to that basis have to match up. But if the components of the vectors match with respect to a basis, it follows that the vectors are equal. These vectors being equal is simply the statement that f times cx plus y is equal to cf of x plus f of y. But that holds for arbitrary x, y, and constant c, which goes to prove to you what? F is a linear map. So now we have shown that F is a linear map. And guess what? the condition star is actually nothing more than the condition for orthogonal matrix written in a different notation. Like, now, so this shows f is linear, right? So this holds for all x and y and c, agree? This is linearity. Hmm? Both of which at once?
Well, the definition of a linear transformation is that the
Oh, yeah, I mean, okay, great, yeah. So if you put c equal to 1, we get additivity. If you put y equals to 0, we get homogeneity. So, yeah.
no, 'cause that was like, there's something that like was in my memory of, and there's a definition of a linear transformation.
Ah, okay, so if f of x then is equal to the matrix R times x, like that, right? Then if you look at f of p dot f of q, we get, matrix R P transpose matrix R Q, which by sock shoes gives me P transpose matrix of R transpose matrix of R Q again. And if you let P equal to UI and Q equal to UJ, this says that, yeah, this is I. Thank you. So if you take UI and UJ, then you get that IJ is equal to R transpose matrix of R transpose matrix of R IJ, because multiplying by the ith row vector and the jth column vector picks off the ijth component in the matrix. And so since that holds for all ij, it goes to show you that the product of the transpose and the matrix is the identity again. Which again proves that, in fact, yes, it's an orthogonal. Now, I must admit, I was frightened by this theorem when I first saw it, because it took me a while to understand what was being said, which is that preservation of distance and fixing the origin implies linearity. That's really very interesting, because we're going from something geometric to something. Yeah, and yet they are, right? So, okay.
Because preserving the distance function is so that, you take constants out and you can pull apart transformation by parts.
Mm-hmm. So, let's see here.
So essentially the theorem is that if you can prove that the distance is preserved, it's the same as saying that it's a linear transformation.
At least for Euclidean distance. I can't speak to other distances. I'm not sure if this is also true for hyperbolics, or other distance functions, but certainly for Euclidean distance functions, true. It's probably true for a relatively wide class of distance functions. But here's the theorem, which says that every, let's say, phi in isom Rn has form phi equal to T composed with R, where R is an orthogonal transformation and T is equal to TA for some A. In other words, every isometry of Rn can be formed by the composition of a translation and a rotation and an orthogonal transformation. And if you dig down into orthogonal transformation, each orthogonal transformation can be written as the composition of a rotation and a reflection. So generally speaking, you have a rotation, a reflection, and a translation. Compose those, you've got an orthogonal transformation. So this means that phi of x is equal to mx plus a for some M in ON. I mean, that's what this means. A line, what? So this is, so the fact that the composition of a translation and a rotation is an isometry, we've already proved, because we proved they're both isometries, and we proved that the composition of isometries is an isometry. So all that remains, and furthermore, so if phi is an isom, right? And phi of 0 is equal to 0, then phi is orthogonal, right? By our previous theorem, which wasn't easy to prove. But if it fixes the origin, it's an orthogonal transformation. What if it doesn't? If not, if phi of 0 is not equal to 0, then f of x equal to phi of x minus phi of 0 fixes 0. Furthermore, f is nothing more than the composition of the translation by minus phi of 0 with phi. And as such, it's an isometry. Well, I subtract off whatever it is at 0, that fixes 0. So just translate, make it 0, go to 0. And when you do that, that makes f of x an origin fixing isometry, which makes it a rotation. So rotation equals to f equals to translation minus phi of 0 composed with phi. So now let's go back to the fact that we had an inverse for the translation. We just do what? Compose with the translation by plus that instead of minus it. And this gives us that phi is equal to the translation by phi of 0 composed with r. Which is, again, the composition of a translation and a rotation, which is the claim of the theorem. And if you look at the matrix of that, it has to have the form, you know, the A in this case is actually phi of 0. And the, I think I got the minus phi of 0 somehow. Well, anyway. Oh, yeah, well, this is fine. But there it is. That's proof of the theorem. So that brings us to describe the set of isometries. And so just to take a step back, let me talk more about, you guys are in abstract, you're in group theory right now, right?
Yeah.
So abstract algebra. So stop and take a look at what we have. We have these isometries, right? We compose two isometries together, we get what? Another isometry, right? The composition of maps, by the way, is an associative operation. So this composition is associative.
We have an inverse.
Translation has an inverse. Rotations have an inverse. I didn't prove that, but you can prove it.
And then
So every element has an inverse. The identity is the identity map.
so that would mean it's a group.
It is, in fact, a group. This is the group of isometries. The group of isometries, in some sense, describes the structure of Euclidean geometry. These isometries are also sometimes called rigid motions because they preserve the shape of objects. So the next thing we're going to do is we're going to look at how this group of isometries